My name is Albert, and I will be presenting something that was just presented like 3 or 4 hours ago. And so if you already saw this and remember every single slide, then you should feel free to take a 5-minute nap. Um, so roboticists dream of unboxing a robot that works in one target domain, such as our home, and can learn new tasks with few demonstrations. And several approaches tackle this goal. One is to only train, the naive way is to only train on target domain demonstrations. These policies require a lot more than just a few demonstrations, which can be infeasible for the end user to collect. Another approach is to collect a ton more data across many different real-world domains to generalize to the target domain. But this can be prohibitively expensive as well. And digital twins was mentioned in a question earlier today in this workshop. But a third way is to construct a digital twin of the target domain, a hyper-realistic digital twin, to leverage abundant simulation data to complement scarce real-world demonstrations. But it's really engineering intensive to do system identification to match a sim environment to the real environment, and real-world physics can be hard to faithfully simulate. And even after all these efforts, a sim-to-real gap would still exist. So can we avoid system identification by using natural language to bridge a large visual sim-to-real gap? Language could help extract abundant semantic information from simulation data when learning from a few real-world demonstrations. We propose doing so by learning domain invariant representations through natural language. Say we have a sim and real image from pick and place with very similar language descriptions. We want to learn a visual representation such that the embeddings of these two images are pushed together so that the policy head can predict very similar actions for these two semantically similar images, namely to open the gripper to place the object. Conversely, if the sim and real image have very different language descriptions, then we want our language representation, we want our image representations, we want our learned representation to pull apart the embeddings of these two images so that the policy head can predict very different actions for these two images. So we do so by adopting a pre-trained fine-tune paradigm where we first try to learn a domain invariant visual representation, visual encoder for sim and real images. So for each image language pair in simulation and real, we encode the images through a learned CNN to get image features, and we encode the language descriptions through a frozen LLM to get language embeddings. And we adopt or experiment with two pre-training variants. A is regression-based, so the CNN must predict the language embedding, the description embeddings for each image observation with a learned linear layer. However, we thought that this might be too strong of an objective, so we additionally experiment with a more relaxed objective, B distance-based, where the CNN must learn to embed the sim and real image embeddings such that their distance approximates the distance between the corresponding language embeddings. So in the second step, we take the visual encoder learned in the first step as the backbone of our language condition policy. We cast Sim2Real as a multicast learning problem between many sim tasks and one real target task. We add adapter modules to process the language instructions, add a policy head, and do BC. We experiment with 3 different task suites of varying difficulty and time horizon, including one with a coarsely simulated deformable wire. And we describe our results here for 100 real-world trajectories. On the x-axis, this represents the 3 task suites, and the y-axis is the success rate. So in shades of blue are the non-pre-trained baselines, which are BC randomly initialized policies trained either with or without simulation data. In red is MMD, which is a classic popular domain adaptation approach. In shades of green are prior works in vision language representations. So this is CLIP and R3M. And in shades of gold are R methods 2 variants, which outperform all the baselines. And these results, especially on wrapped wire, show that language can bridge wide sim-to-real gaps even when there are deformable objects. We also decreased the number of trajectories in the real world that we assume access to 50. And our methods are still outperforming baselines, and the same trends hold at 25 real-world trajectories. So these are some of our policies rollouts on two-step pick and place. And some failures involve not being able to start the second step after finishing the first step. And this is our policy doing wrap wire, and failures involve grasping imprecision and premature gripper opening. In conclusion, we see that language can bridge a wide visual sim-to-real gap by learning domain invariant representations with 25-to-1 on real-world trajectories. And our method can open the door to leveraging low-fidelity simulation data to improving sim-to-real transfer onto formable objects. Thanks.